Hi, welcome to today's TEE tutorial by Tau Beta Pi, University of Florida Alpha Chapter. My name is Maddie Sciullo, and I'm a third-year PhD student at the University of Florida. So one of the things that I'm going to talk to you about today is the P-N junction theory. And this theory is one of the main reasons that got me interested into doing my PhD research within solid-state devices. So let's get started. One of the things I like to do when I give a lecture is give a realistic application. So P-N junction theory is the basis for diodes. And so you guys will probably have seen diodes within your circuit classes. And so this is the symbol for a diode. What's really interesting is how the diode has current flowing only in one direction. So we're going to explore why. P-N junction theory, right? So let's break that down. We have two types of semiconductor. So we have a P type and an N type. And what does that mean exactly? So you may recall from previous lectures that P type is where you have more acceptors, which are holes, so more positively charged ions than negatively charged ions. So for now, I'll draw a bunch of plus signs indicating that there are more positively charged ions in this material. And so the same goes for N-type. With N-type, we have now a reversal of charges. So now we have more negatively doped ions. So we have more electrons that are available in this semiconductor. So the interesting part when it comes into play when these two types of materials that were separate and nothing was going on actually touch now and make this junction, right? So we put these two materials together, and now it allows this really cool stuff to go on. So first, these free electrons, or these free holes, now have the ability to move in between the two materials. So what you may recall from one of Newton's laws that or thermodynamics, how things want to spread evenly, or how a force or an object stays at rest until a force acts upon it. So putting these two materials together force these two materials to interact and therefore spread and try to reach equilibrium. So we'll talk about one important factor, which is diffusion. And so again, we have these free charges. If you may recall the idea of diffusion, but in a more realistic sense, if I were to spray perfume in a classroom, the perfume will spread throughout the air molecules and try to equalize itself. So the idea that these particles can move from one side to another in order to reach equilibrium. We also have this idea of distance. If I am closer to the perfume, I will be able to smell more of it. But if I'm on the opposite side of the room, it may not even get to me and I may never smell it. So these free particles, these acceptors and donors, actually, because they're closer to this junction, have the ability to move more from one to the other. And when they do, they leave an opposite charge there. And this charge is fixed. And so what we see happen is are these lines of charges at this boundary that are fixed. And if you recall from previous learning in physics, where there's fixed charge, there is an electric field. And so this built-in electric field is what causes the one-way direction of this current in a diode. And this area here is referred to as our junction length. and our depletion region. And for notation, we note the sides of the depletion width with respect to the actual value of the width from a time or from a coordinates system, because you'll see later on that the sizes of these depletion regions on each side of the materials has an effect on this charge distribution and the electric field built inside of it. So, more into what happens. Let's look further into it from a band perspective, energy band perspective. So if I have two materials next to each other, Okay, so let's draw the energy band diagram for this p-n junction. So if you recall from previous energy band diagram lectures, you'll remember that for a p-type material which has more acceptors, its conduction band is going to be higher than its, the Fermi level is going to be closer to the valence band than it is to the conduction band, because we have less electrons filling in these energy bands. And then the opposite for n-type, right? Because we have more electrons to fill these energy bands. And you'll recall that whenever you're doing an energy band diagram, the Fermi level has to be flat. So you draw the conduction band and the valence bands according to the material type and with regards to its spatial difference from this Fermi level. So looking further into this depletion region, right? Because this is where the magic happens. So let's look further into that. And you'll see that here, around this junction, we have a difference in bands, and specifically in potential. So you have to connect these two continuously, and we get this band bending that happens. This change in voltage, it correlates to the electric field. And so let's look further into what this mathematically represents, right? How can we quantify this built-in electric field or this potential value? So if you'll recall, energy bands are given in electron volts. And this stands for the charge of an electron, right? And then we have potential. So the way we quantify this built-in field is the difference in these bands. From the difference in the conduction band or in the valence band across the two materials. So first, let's just look at one case where we look at the difference in the conduction bands. And this is Q phi BI. Phi BI is normally denoted as the potential for the built-in voltage. And Q, again, is the electron charge. And so just arbitrarily for math's sake, we're going to say that the potential difference from the conduction band to the Fermi level in the N region is quantified by QA, A being some arbitrary potential that we don't know. And likewise over here, but you'll notice that B is much greater than A. And so we can use this to say that the potential of the built-in voltage is equal to the subtraction of the potential in the P-type and the potential in the N-type given respect to Fermi level and the conduction band. So our Q's cancel, and now we have phi B I equals BA. So the potential difference from the conduction band to the Fermi level in the p-type region, subtracted from the potential from the difference in conduction band and Fermi level with the n-type region. Okay, so how can we use this? What other mathematical models do we have? If you'll recall from previous chapters, you know that in the n-type region, so right now we'll just call it n region, we have our concentration of electrons is equal to the number of donors in the material. And this is allowed because it is an n-type region, right? So the number of donors is going to be much greater than the number of acceptors. Therefore, we can assume that the number of electrons is equal to the number of donors. And from there, we also have that it equals the density of states equation, where we have NC, which is a constant from density of states, with E raised to the negative QA. So again, this potential change here over KT, which are Boltzmann constants. And then also for P region now, we have to go the opposite way. We have to say that our number of electrons is going to be the intrinsic value Ni squared over the number of donors. And you'll recall that this is from your P equals Ni squared. And so if we're solving for N, Na, that's where I went wrong. Okay. See how you double check? I caught myself. So, since it is a p-type material, which means that it is doped with acceptors, we can say that our concentration of holes is assumed to be the same value as the number of acceptors. And so from this golden rule, which you should have memorized by now if you don't already, is the number of the concentration of holes times the concentration of electrons is equal to the intrinsic value of the material squared. Okay, so moving further with this, we can also do density of states with this again. And from here we get NC equals the same value as before, but with QB. And so using these two equations, equation 1 and equation 2, we can simplify further to get our B and A, right? So let's set this one equal to B now. Oh, I'm sorry, A. Which is KT over Q, ln of ND. Yeah, and NC over ND. So our potential from EC to EF, so the conduction band to the Fermi level, is equal to Boltzmann constants, K with temperature and the charge of the electron, times ln of the density of states divided by the number of donors. And similarly, B will be the same constants, but since we don't have ND now, we have to rearrange where we get ln of number of acceptors times number of donors over the intrinsic value squared. And so this stems from setting these two equal and solving for B, and the same for this as well, but solving for A. So now we can plug these two into our main equation and figure out the built-in voltage potential value. And so what's really interesting is if I were to apply a voltage the opposite way, right? I need a big enough voltage, theoretically bigger than the built-in voltage, to have current flowing. Because what happens visually are these electrons need to have a certain energy to climb up this potential difference. And so once you apply a big enough voltage, then you will have current flowing in the other way. And so this is a great application for leakage problems. So if you are trying to prevent leakage from your device, you can set up a diode because leakage will be approximately less than the built-in voltage. So you can prevent leakage from going to other components in the device. And that's it for today. So I hope you guys learned a lot, and make sure to follow TEE for more tutorials.